Hello, this is the beginning of Chapter 9, which involves infinite series. In our first section, we are going to talk about sequences. We can get pretty formal with that definition, but putting it simply, a sequence is simply a list of numbers written in a specific order. And we use subscript notation to identify each of the terms. So each one of these would be a term in the sequence, and they are denoted by a sub n, where a sub n is the nth term of the sequence. A sub 1 is the first term, so on and so forth. So we might denote the entire sequence using this notation here. The first example is really not terrible, and I think you might like it because of that. It says write the first 5 terms of the sequence with this given nth term. So basically, this is like the formula that we'll use. So what we want to do is we want to find a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, because this will give us the first 5 terms of the sequence. So again, this subscript represents n. So anywhere we see an n, we are going to plug in a 1 in the first case. So negative 2/5 to the power of 1 is simply a negative 2/5. Moving on, now n is 2, so negative 2/5 to the power of 2. We square everything here and we end up with 4 over 25. Moving onward, we have negative 2/5 cubed. This is a negative 8 over 125. Here, negative 2/5 to the 4th power. This will be a positive number because we have an even exponent. So 16 over 625. And then finally, negative 2/5 to the 5th power. This result will be negative because it's an odd exponent. And there are the first 5 terms. In the next example, it is the exact same thing. So why don't you go ahead and pause this video and see if you can come up with this result. So just like before, we need to find a sub 1 first. The only difference here is we are going to be plugging 1 into 2 places. So we will have 3 times 1 over 1 plus 4. This gives me 3/5. The second term is found by taking 3 times 2 and dividing by 2 plus 4. On the top I have 6, in the bottom I also have 6, so this results in 1. The third term is 3 times 3 over 3 plus 4, which is 9/7. The fourth term is 3 times 4 over 4 plus 4, giving me 12 over 8, and this simplifies to 3/2. Finally, the fifth term is 3 times 5 over 5 plus 4 is equal to 15/9, and that results or reduces to 5/3. So that's the first part of this section, writing the first 5 terms. I'm pretty sure that you will think that that is doable and perhaps a little enjoyable as well. The next type of example we will see is a sequence that is defined recursively. And what that means is we need to know a term or maybe a couple terms before the term in question. So what that means basically is a very famous one is the Fibonacci sequence. And so what you need to know the terms before it, or the term before it. So if I'm given the first term and I'm given the k plus 1 term. What this means is I need to know a sub k in order to find the next term. Okay, so this is like the previous term. Okay, now this sounds a lot more complicated than what it is. Okay, so if I want to find the first 5 terms, hey, guess what? We already have the first one and we are super happy. So now we're going to move on to the second term. Well, looking at this formula, a sub 2 is found by taking 1 plus 1. So k is 1, which means in our formula, we are interested in 1/3 times a sub 1 squared. And a sub 1 is simply the first term. So this is 1/3 times 6 squared, which is 1/3 of 36, which is 12. So really all we are doing is we are plugging in the previous term right here. So that means if I want to find the third term, instead of 6 here, I'm going to plug in 12. So 1/3 times 12 squared, because this was the result of the term before this, the previous term. So this is 1/3 of 144. This gives me 48. Okay, so again, I took this, plugged it in here. So now, to find the fourth term, I use the same formula, but I'm plugging in the previous result, which is 48. So 1/3 times 48 squared. This is 1/3 times 2,304. This results in 768. Okay, so now I'm moving on to the next term. So I need 768 to find the fifth term. So I'm going to plug in 768 here. So 1/3 times 768 squared, it's a doozy. 589,824. I did that in my head because I'm that great. Okay, so when I multiply that by 1/3, I get 196,608. So I found the first 5 terms of this recursively defined sequence. And if I wanted to list them out, I could certainly do so. Oops. And there they are. So in order to find the second term, I need the first term. In order to find the third term, I need the second term. In order to find the fourth term, I need the third term, so on and so forth. Okay. So sometimes we may want to find a limit of a sequence, and sometimes this is hard to wrap your head around because all of these sequences, they are infinite sequences. They go on and on and on and on. And you might think, well, how in the world can there be a limit of something that goes on and on and on and on? Well, let's take this graph, for example. Okay, if I have this graph, remember a limit is the intended height of a function. Well, as the limit approaches infinity, so the limit as x approaches infinity of this function, well, as x gets bigger and bigger and bigger, the intended height of this function is 0. So even though this function goes on and on and on, there's still a limit, and that's what's going to happen here. So the formal definition is written here. But basically, these terms could potentially converge to a certain number. So if there is a limit that exists, then we will say that the sequence converges to that number. And if we look at the sequence 1/2 to the power of n, that's what we have here. I'm sorry, that's different. I'm sorry, it's 1/2n. I apologize. You can see that the denominator is getting bigger and bigger and bigger. So this is going to approach 0. So we will say that this sequence converges to 0. So here, if the limit of a sequence exists, then the sequence converges to that limit. On the other hand, if the limit of the sequence does not exist, then we will say that it diverges. And this is some important information. Now, the thing you need to kind of come to terms with is that limits are back, and you might want to review it because when you learned limits, it may have been a little frightening. And now that you are more mathematically mature, if you will, I think that you will think it's a little more manageable. So this is just a brief illustration of a limit of a sequence and how that limit of the sequence will kind of bounce in between these values. You can pause this and kind of read through this a little bit if you'd like. So in this chapter, we will have a ton of theorems, and a lot of them are theorems that we're going to be referring back to. So it might be helpful to maybe make a list of the theorems or be able to have a place where they are easily accessible. So the first one is the limit of a sequence, and basically I talked about that. Basically, if I want to find the limit of a function, it's just like finding a limit of a sequence. And I'll show you some examples of these, and I think it will make a bit more sense. So there are different ways in which a sequence can fail to have a limit. And one way is if the terms increase without bound or if they decrease without bound. So we'll see some cases where each of these things occur. Before I can jump into examples of what I'm talking about, here's theorem 9.2, so yet another theorem. And this should be pretty straightforward, so I don't know if this is one that you necessarily need to refer back to, but it's just saying, hey, if the limit does exist for this sequence and the limit exists for this sequence, then you can have a scalar multiple, you can add the limits, you know, they're pretty straightforward. You can multiply, so on and so forth. Okay, so the first example I want to address involves factorials. And factorials are those fancy numbers that have exclamation points. For example, 4 factorial. Now, please do not confuse this with 4, like if you are golfing with me, for example. Okay, so this does not mean like 4 really loud. Instead, this means 4 times 3 times 2 times 1. 0 is excluded from this little series here because anything times 0 is 0. Okay, so if we see 4 factorial, it's 4 times 3 times 2 times 1. If we see 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. 0 factorial is always 1. And we are not going to get into the reasoning behind that. That is for a higher level math class. Okay, so What I want you to notice is the following. If I'm looking at this first group here, this 4 factorial, if this is n, then this is n minus 1, and this is n minus 2, n minus 3, okay? If this is n, we have n, n minus 1, n minus 2, so on and so forth, okay? So, if we are asked to simplify this, we have n plus 1 factorial on the top. And what our goal is to cancel out this denominator if possible. So that means I need to somehow rewrite the numerator to get it down to the denominator so it can cancel out. So what I can do is I can rewrite this factorial. N plus 1 factorial is the same thing as saying n plus 1 times n plus 1 minus 1, because that's the next term, right? And when I have n plus 1 minus 1, well, plus 1 minus 1 cancels out, right? So that's really n. And then my next term, if this is n, then my next term must be n minus 1, right? Now, I want to show you something. I need to put a factorial here, and this is why. I can write 6 factorial as 6 times 5 times 4 factorial if I want, because 4 factorial is the same thing as saying 4 times 3 times 2 times 1. So any factorial you are dealing with, you can stop anywhere and write it with the factorial there. Which I kind of think this stuff is pretty interesting personally. Okay, so I knew to stop at this term because this term needs to cancel out. So now I can cancel out this and this. So I am simply left with n plus 1 times n. Because of this and this is all that's left. If I want to distribute that n, I certainly can. So I have n squared plus n. Okay. So this might be something pretty new to you, and factorials will come up a little bit in this chapter and then in future math classes also. So you might want to kind of make sure that you spend a little bit of time with it. Let's look at the next example. So what I want to do is I want to take this numerator and break it down to different terms until I can stop at 3n. Because if I can stop at 3n factorial, it will cancel out. Okay, so let's give that a try. So remember, in a factorial, all we do is we subtract 1 every time. Okay, so I'm starting off with 3n plus 1. So my next term is 3n plus 1 minus 1. Okay, well, what happens when you have a plus 1 and a minus 1? They cancel. So really, this is 3n. So I'm going to stop there. And this is over 3n factorial. So the 3n factorials cancel, and I am simply left with 3n plus 1. That's all there is to it. Okay, so this gets to the good stuff. It says determine the convergence or divergence of a sequence with the given nth term. If the sequence converges, find the limit. Okay, so basically what we want to do is figure out, so this sequence goes on and on and on and on and on forever. So n is approaching infinity. Okay, so what we want to do is figure out if when n approaches infinity, does this sequence converge or diverge? This sequence will converge if the limit exists. If the limit does not exist, then it's going to diverge. Now, what some students like to do is they like to kind of see the first few terms. You can certainly do this, but you don't have to. So in this example, I have 1 minus 1 over 1, which is 1. This gives me 0. The second term is 2 minus 1 over 2 factorial. 2 factorial is 2 times 1, so this is a half. 2 minus a half is 3 halves. The third term is 3 minus 1 over 3 factorial. This here approaches 0 as, okay, I went too far. So this is 3 minus a sixth, so on and so forth. So you want to see what this sequence is approaching. Now, writing all these terms down may or may not be helpful, but I just want to illustrate the following. Now, these numbers here are increasing, but what's happening here? Well, this ends up approaching 0, right? Because the denominator is growing faster. So this term here is going to approach 0. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8 to infinity. So the limit as n approaches infinity of this here, well, let's analyze this. So, we can see what's happening by writing the terms, so I guess it can be helpful. If I plug in a bigger and bigger and bigger number here, it just gets bigger, but this approaches 0. So this limit is just increasing without bound, so the limit's infinity. In other words, the limit does not exist, and this tells me that this sequence diverges. Okay, so you can write a list out the sequences, the terms of the sequence if you want, but sometimes it's not helpful. For example, in this, if you start listing the terms, you'll find that it's 0, 1/2, 0, and it kind of bounces around a little bit. So it's not super helpful. So instead, what you can do is you can evaluate the limit. And this is why I mentioned, hey, limits are back. So again, we want to see what this function is approaching. Okay, and remember that by the definition of the limit, whatever this function, whatever the limit as n approaches infinity, whatever that is of this function, that's the limit of the sequence as well. So the limit as n approaches infinity of 1 plus negative 1 to the nth power over n squared. Okay, you guys, so, this could blow your mind. I don't know, but chances are you're not going to remember all of these limit rules. Okay, so baby steps to get back into it, and you'll be fine. In this case, we can't use direct substitution. It's just not very helpful. So instead, what we're going to do is we are going to multiply by the conjugate of the numerator. So we're going to multiply by 1 minus negative 1 to the power of n on the top and the bottom. Okay, so this will have to be FOILed, and then we'll distribute here. Okay, so remember when you're dealing with limits, you need to continue to write this notation in front. When we FOIL this, we have 1 minus, so this and this, plus negative 1 to the power of n minus a negative 1 to the power of 2n. Okay, because if we have the same base, we add the exponents. Same base, add the exponents to get that 2n. Then in the bottom, when we distribute this n squared, we have n squared times, actually I take it back. It might, you can either distribute it or not. It's actually easier to not, and I'll show you why in a second. So leave it as is. Okay, in the top, these middle terms cancel out. And then this here, since this is an even exponent, this is always even because it's multiplied by 2. Okay, this is always 1. Negative 1 to any even power is 1. So I have 1 minus 1, which cancels out. So I have the limit as h approaches infinity of 0 over all of this. And I didn't distribute because I can see in the future, and I knew that I could stop. Remember, anytime 0 is in the numerator of a function, this results in 0. So in this case here, the limit is 0. Since the limit exists, this sequence converges. Okay, let's look at some more examples. Okay, so just as before, it says determine the convergence or divergence. So here again, you can list out some terms if you want. It doesn't really matter, but I kind of want to remind you of some of the rules for limits instead. So we want to find the limit as n approaches infinity of this function here. And I want to blow your, that is a 3. I want to blow your mind again and show you this. Now, in this case, multiplying by the conjugate doesn't get you anywhere because it actually complicates the radical. So instead, what we want to do is we want to try to eliminate this if possible. And the way we're going to do that is we're going to multiply the top by 1 over the cube root of n. Because if I multiply this by 1 over the cube root of n, then in the numerator, the cube roots of n go away. Now remember, whatever I do to the top, I need to do to the bottom, because this is just like multiplying by 1, which does not alter our function at all. Okay, so looking at this, like I mentioned, up in the top, I end up, these guys cancel out, and I end up with 1. Now in the denominator, when I take this times this, I get 1, plus this times this, I get this. Okay, now typically we don't want to have a fraction within a fraction. Okay, but I want to show you something. Applying the limit now, I only have one place to consider, and that's right here. So for n, I am plugging in bigger and bigger and bigger and bigger and bigger numbers here. So this is getting bigger. This denominator is approaching infinity. Okay, so that means 1 over infinity, that means this term will go to 0. So by applying this limit, I have 1 over 1 plus 0, which is 1. So since this limit exists, this function, I'm sorry, not function, well, the function or the sequence converges. Okay, same thing here. And you can see how this factorial is coming up quite a bit. So just like before, we want to find the limit as n approaches infinity of n plus 1 factorial over n factorial. So I want to simplify this. Okay, so good thing we practiced before. So I need to break this top part down to get to n factorial, which will cancel out. So if I have n plus 1, then the term after it is n plus 1 minus 1. And sure enough, those cancel and I'm left with n factorial all over n factorial. These cancel out. So all I'm dealing with is the limit as n approaches infinity of n plus 1. So if this is infinity, infinity plus 1 is infinity, which means this limit does not exist, and therefore this sequence, does not converge, it diverges. Okay, so you can see that limits are really heavy in this section, which I'm sure you're really happy about. So another theorem that may come up is called the squeeze theorem for sequences. There are different squeeze theorems in mathematics. This one involves sequences. I'm not going to do an example of this, but there is an example in your text on page 591. So if you want to take a look at that, you certainly can. This next slide talks about how sometimes you'll see different patterns, and it's easy to identify what that rule is, if you will. And sometimes it's easy, sometimes it's hard, and I have found that students can either identify the pattern very easily, or students struggle with identifying the pattern. And let's take a look. So in this example, it says write an expression for the nth term of the sequence, and then determine whether the sequence you have chosen converges or diverges. Now, there can potentially be a few different answers for this. We kind of need to be careful with this. But what's happening is we can see that this sequence goes on and on and on. And I want to know what is the formula for this? How did we come up with each term in this sequence? So if we want to find the nth term, what we're looking for is the formula for a sub n. Now, one thing to address is that this sequence alternates signs from positive to negative, so on and so forth. When that happens, the way we denote that is -1 to the n plus 1 power. Okay, and let's just look at that for a second. If I'm looking at the first several terms of just this, I have -1 to the 1 plus 1. -1 to the 2 plus 1. Okay, well, what happens there? Well, this is -1 squared, which is 1. This is -1 cubed, which is -1. This is -1 to the 4th, which is +1. So this is what we use to alternate the signs. Okay, so this piece here is for alternating signs. Okay, oops, sings, good Lord. Alternating signs. Okay, so now we want to see what's happening with the number itself. And one thing to notice is that we have fractions, okay, and in the numerator, we always have 1. So we're going to multiply this -1 for the alternating sign by 1 over something. And we need to figure out how we get, now we can put a 1 here. How do we get from here to here? How do we get from here to here? How do we get from here to here? Well, remember we're dealing with the value of the term of the sequence. Okay, so here n is 1, n is 2, n is 3, n is 4. So if this is a sub 1, a sub 2, a sub 3, a sub 4, what are we doing with this number to get this? Well, we're squaring it. So whatever n is, we are squaring it. And that's how we get our formula. So we can put this over 1, multiply across the top, across the bottom, and we can write this as -1 to the n plus 1 over n squared if we want. So this is the expression. Okay, so from here, we're asked to determine whether this converges or diverges. So we find the limit as n approaches infinity of this, -1 to the n plus 1 over n squared. Well, let's analyze this. We already know that this is going to be positive or -1, right? We already established that. So this limit is going to have either a positive or -1 on top. And if I plug infinity in down here, infinity squared is infinity. Well, if this is getting bigger and bigger and bigger, this fraction is approaching 0. So the limit exists, it's 0, which means our sequence here converges. Okay, that wraps up section 9.1. I hope you enjoyed this.